All right, welcome back. We are Game 3001, that's Artificial Intelligence, in the winter 2021 semester, and it's week 10, but it's lesson 9 of our broadcast, and it's part 1. So it's kind of weird here at George Brown. We have it's kind of week 9 from a lesson perspective. We've only done 9 weeks of lesson, but because you have that break. But it's actually calendar week 10 for us when it comes to the way it is. So this is actually officially week 10. And I always get mixed up like this because everyone has different ways of counting semesters and so on. And that's fine. So let's get into it. So this week, Lab 7 is due Sunday at midnight, like normal. Also due is not this Sunday, but next Sunday, Assignment 3, which is your first behavioral assignment with AI. That's due next Sunday at midnight. Again, guys, please sign up for A3 groups. And if you signed up for the wrong group, and I got some information or emails that you guys signed up for the wrong group, during lab today and on Friday, we can fix it, right? If you're signed up for the wrong group, again, I made different groups. I made A3 groups and A4 groups as an example. Again, I've made groups for all the different labs. And the reason why I want to do this is to give you guys flexibility, but it also means that you need to do a little bit of extra work for you and sign up for your A3 groups, or else you will not see assignment 3. That would be bad, right? So please make sure. And if you signed up wrong, let me know during lab and I'll fix it. Okay. We're sitting at week 10 officially from a calendar week 10, but lesson 9. And we're talking about behavior trees and directed acyclic graphs, which is something that we're dealing with. Next week, we're looking at state machines, and then that's when assignment 3 is due. And then we're into more interesting topics, goal-oriented behavior and machine learning for games, reinforcement learning, all that stuff happening over the next few weeks. All right, so that's what's coming up. And then with your final test being the last test. So we're talking about behavior trees this week. One thing to note is that behavior trees, there's actually a little article that I put up on from Gamma Sutra, I'll be okay, I can speak today. That's up on Blackboard, and it's here if you want to take a look. It's really an interesting article on how behavior trees work. Again, it's a little dated. It's from, like it says, 2014, but actually it's really good in terms of the way it expresses everything. So I think this is really good to look at. Gamma Sutra they have some great articles on AI and game mechanics and a bunch of other stuff. So take a look at this one. I think it's a good one to read, and maybe we'll look at it a little later as well to help us with understanding. All right, so let's get back to the PowerPoint. We talked last week about decision trees, and decision trees use, like we talked about before, this structure where you have a binary tree, right? Remember binary trees from last week? We have a root node as an example. I'm just going to draw the nodes here with these blocks. So there's the root node, and then the binary tree has a left branch and a right branch. And as an example, then we have additional nodes, right? So that's how the balanced binary tree looks like. It's balanced because we've got 2 subtrees, this tree here and this tree here, and there's subtree on each side. And if it's completely balanced, then you're going to see that as it goes down the line, it's going to have, again, 2 subtrees here, or, as an example. And if you have trees, this is just a review from last week, then, here's some ugly nodes that I'm making that are irregularly sized, but you get the picture, all right? So when we start labeling them, then we can sit there and say, well, this is the root node, right? And this is just some naming. This is a root node. And we also talked about this idea of having trees. We have our subtree on the left. This is a subtree. Okay. And the subtree is basically another little tree with its own root, right? Kind of stuff, right? We also talked about edges and tree height, right? So notice that if my tree height is 2, right? Then I have it's n to the 2, right? Okay, here's something. It's 2 to the n nodes, where n is the tree height, right? So if I did that, if n is equal to the height of the tree, right? And this is just a little bit of math, right? Let's just think about this. If n is the height, and in this case, if n is 2, n is equal to 2, right? Then how many nodes, how do I find the equation for how many nodes I have for a balanced binary tree, right? As an example, when I have a height of 2. How many nodes do I have? I have 1, 2, 3, 4, 5, 6, 7. All right. So it's like I have 2 to the n, right? 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3, if it was a height of 3, is 8, right? So then how do I have, what is this thing? 2 to the n minus 1? Okay, well, if that's true, 2 to the n, which is 2, if this is truly a height of 2, this, height of 2 edges here, then that would be really 2 to the 2, 2 to the 1, right? 2 to the 1 is just 2. So I don't have 2 nodes, right? That can't be it. That's not enough, right? So that's something else, right? So remember, because I also have my root node, right? So my root node counts as something else. So whatever my height is, and I add 1 because of my root node. So this is not really the height. So how do I find the height of my tree? And if we look at, number of nodes of tree of height n, how do I find that out? And it says relationship number of nodes and the tree, right, where my height is 2. Here's the equation. The idea of 2 to the h, the height plus 1 minus 1. All right, that's interesting if that works. Let's see if this works for us, if that makes sense. So, okay, 2 to the n. So if the number of nodes is 2 to the n minus 1, right? And then add plus 1 at the end, right? Remember, order of operations, right? And that if that's the total number of nodes, so number of nodes, if that makes sense. Let's see if that makes sense, right? If number of nodes is 2 to the n minus 1 plus 1. So n minus 1. So if I took n, I know, Shabam, but let's do this one first. So 2 to the n minus 1. So 2 to the n. If I did this, right? And n minus 1, so 2 minus 1 is 1. 2 to the 1 is 2. And then plus 1 is 3. So that is wrong. Okay? Okay, so that's not the right one. And let's do what you said and do it right. Okay, so let's do what you said. And I'm exploring these little algorithms because we need to figure out sometimes, the number of nodes. I want to kind of calculate the number of nodes. So what if instead of 2 to the something minus 1, so I want to find n plus 1, right? So n plus 1. Let's put that plus 1 in there. And let's make it so it fits. 2 to the n plus 1, and then minus 1. So we'll just put a minus, right? So we'll make a dash for the minus. Why not? It's just still the same. And maybe if you make it so it's dark, some people are still showing up. So this is good for a review perspective. So 2 to the n plus 1 minus 1. Okay, let's see if that works. So 2 to the n plus 1. So 2 to the 3, right? So if that's the case, n plus 1, so 2 sides plus 1, that's 3. So 2 to the 1 plus 1 is, or 2 plus 1 is 3. 2 to the, it would be 8 minus 1 is 7. So that is the right way of doing it. That means the number of nodes then would resolve to, in this case, to 7. All right, so that's how we calculate the total number of nodes that we have. So this is the total number of nodes. How about traversal? When it comes to trees, we want to start traversing trees, right? How do we traverse the tree? So I'm starting at the root. And remember, we talked about this as recursive, right? So recursive. So I start off and I go, okay, so let's start off. And I want to go left first. Let's start from the left side. So if I start from the left side and I start counting, I go, okay, cool. So there's a tree here. Let's go to the left side. So the left side starts down here. And this would be the like kind of node, let's say A or whatever. Let's just say this is node A. And this is the first node that gets loaded in, right? So I start off with node A, and then I go back to here, and this is node B, right? Actually, it doesn't go here. It goes to the next one, the next subnode or subtree. So it goes B over here. These are leaf nodes. Remember, these are also things like that we should probably call them. So leaf, subtree, these are leaves, right? Each one of these bottom ones, but doesn't have any more kind of subtrees. So left and right nodes are null. And that's what a leaf is. A leaf is both left and right nodes are null. Okay, and I'm going to say null because for us, when we're programming, that's what it means. Okay, so we have no left and right nodes. They're null or null pointer for us. Okay, and that's cool. So then I'm start counting. So then A, B, then I go over here, right? And I count this as C. If I was going to count this. By the way, there's different ways of counting and displaying the tree. Okay, A, B, and then C. That's weird, right? Shouldn't not this be instead, if I was going to count stuff properly? And by the way, counting is a way of traversal as well. I'm going to go here first, then I'm going to go to here, and then I'm going to put this in place. That's what I'm saying. And then from here, I'm going to go here, I'm going to go here, and then from here, I'm going to go here, and this is going to be D. I'm stating this because it depends on how you see. This is kind of the order that I'm doing it in order, okay? So then I'm going to say E, E, and then finally F. Is this the right way? And then finally G at the top. So why am I counting this way, right? Well, it depends on how you look at the structure of your recursive program, right? We're starting off, we say, okay, so go to the left node. If there's a left node, go to the left node. Does the left node exist? Go to the left node. Does the left node exist? No. Name yourself. Because if there's no left node, because we're assuming that we have a binary tree, right? A balanced binary tree, then there's no right node. If there's no left node, there's no right node. So then, therefore, this mark yourself as A. Cool. Go back. All right. We've done the left node. Now go to the right side. Okay. Cool. Is there a left node? No. There's no left node. Mark yourself as B. Cool. Go back. Left node and right node are marked, right? Mark yourself as C. Cool. So somehow it needs to know which one it is. In fact, if you think about this, this would be 0, 1, 2, right? If you talked about this in number or ordinance, right? It's kind of inverted, isn't it? Yeah. So are we just passing a Boolean about whether it was null back to the recursive function? Yes. Right? So now I come to here. So now it says, okay, here, I'm here, and I've done these two things. I've marked myself. Okay, go back up here. This is marked. Cool. Mark this side. Do I have a left node? Yes. Go to that left node. Do I have a left node? No. Mark yourself as D. The next one after this one. Right? Cool. Go back here. Okay, we've done the left node. Do the right node. Mark yourself as E because there's no left node. Okay, go back up here. Left node and right node done. Mark yourself as F. Okay, go back to the root. You're marked. Go back to the root. Root. You know what? Left node and right node are marked. Mark yourself as G. And that's how it would traverse, right? If I did it this way. Okay, going with the right side, left side. Alternatively, I could say I want to do right side first. I want to do the rightmost subtree as opposed to the leftmost subtree. Okay, we're just talking about tree traversal here. Okay, so I've kind of marked these things. So this is how I could go. I could go down in here and whatever. Here's another thing. Once this is a way of traversal. right? Neil says whatever's the left choice. Yeah. So this is a way of traversal. But what about loading the tree? So one thing we're going to talk about today in lab, right, is an example of loading the tree. Okay, so we need to load the tree. First we have a tree structure, okay, and the tree structure is made up of nodes, right? So let's just get rid of these things for a second, okay? And I just want to conceptualize. So the first thing we want to do, guys, whenever we get together, is do a little bit of conceptualizing, because we can't code without concepts. All right, we know how many nodes there are, as an example, and we know the total number of nodes we have to traverse based on the height of the tree, right? Height of tree is how many connections, right, that it has, how many edges that it has to the leaf, to the leaf node, okay? So this would be a tree height of 2. 1, 2, okay? If I didn't have any edge nodes, then the tree height would be 0, height of 0, which is just the root. It's a stump, the stump of a tree, like in Valheim, stump, right? All right, so yeah, but what happens if we want to this kind of create a tree structure? Well, we need, for a tree structure, we need a node, right? So we need a node class, right? And what does that node class look like? Let's think about this for a second. If I have my node class, what stuff do I need? Well, I need a left node inside my node class, left, and I need a right node, right, and I need a parent node, parent. All right, I need those 3 things. Okay. These are all references to other nodes. These are all nodes themselves. So node has 3 nodes as references, right? And if that's true, if my left node and my right node are null, then we can say that we also have a property that is leaf should be something of a property, should it not? Right? Is leaf is something that is true or false. So that's a Boolean. These are nodes, right? So this is node, right? And we're just going to put it like this so we know what it is. Pseudocode, right? It's a node. This is a node, right? So it's a node reference. I'm just putting it like this so you see it, right? This is a node reference. Okay, I'm building this out with you guys, like writing it on the board, all right? And is leaf is a Boolean, right? Again, it's just pseudocode we're writing here. Okay, so this is Boolean, right? So that's a node class so far, right? Node class has left, right, parent, and leaf. Okay, that's what it has in there as well. That's the nodes. But remember, we also have, we're in a decision tree. If we're going back to decision tree, we also have some kind of data, right, that we have to pass back up to the root node, right? So it's a question mark. One thing is when we build the tree, if I was to build the tree up, then what I want to do is I want to add both the left and the right nodes in order for me to make this this root, as an example, into more of a tree, right? Because if it's just this one root, so if my decision tree has only the root, then there is no decision. It's just like literally you just do the same thing over and over again, right? Now that's also possible. It's not impossible for you to have this, but when I'm building up a tree, right, then I need to be able to add a node to the tree, right? So basically I have to have some kind of function to do that. So my node is this. But what about my tree class? So here's my tree class. Forget decision tree, behavior tree, whatever. We're just thinking about data structures right now. All right, so here's my tree. A tree is made up of nodes, right? It's my tree class. And my tree is made up of nodes. Okay, so it's a bunch of nodes. I at least have a couple things. I might have some kind of number of nodes I keep track of, right? But I have to have some methods to add nodes to the tree. So maybe I have a add node, right? And I can't add a node by itself because remember we want to make a binary or a balanced search tree. We don't have to, by the way, but I'm definitely going to have some kind of add node method. So this is a method, and it's going to return void for now, right? So we're going to say a method that returns void that is a, that allows us to add nodes, okay? I don't know if when we build up a tree, when I add nodes, so I have a tree, I add nodes, nodes, I add the node, right? And each node, right? I mean, it's pretty simple what nodes can do. They just have the ability for you to have left and right. I can make references to the entire tree, right? I can add a node, and when I add a node, I add one of these, left, right, parent, leaf. When I add a new node, whatever that is, the node itself can be configurable, right? So it's not just left, right, parent, or as leaf, but the node can have its own subtype. So what if there's different kinds of nodes? Like, for example, it's a decision node. Let's make it a really simple decision node. And the decision node, it kind of is, it derives from node, right? It's a type of node. So what decisions node look like? So instead of it adding a node, and let's just comment this out. Again, I'm building this up with you guys so we're thinking about it. So because it's going to come up in a second when we start thinking about behavior trees. You're like, wait, we have a decision tree's got decision nodes. Okay, no problem. But what about other types of trees, like a behavior tree? So add node, then, it gives us a couple of additional things. It takes in a decision node if we're making a decision tree, which is a type of node, right? That's what it is, okay? And it returns void. Okay, that's what it is. So this is the complete kind of thing. So we take a decision node, and we're going to kind of crap out here. So let's see if we can reorganize ourselves. Just because I made it a little bit too tight, but who cares? We can fix this issue as we draw, no problem. So I want to grab this thing and I want to move it. So like this, and then let's grab this whole thing here and move that. So the tree class then can have some kind of add node function, which takes the decision node. It has to be of type decision node. And the decision node is a class, again, class. All right, so this class of decision node, which is of type node, right? It has some kind of execution function that it does. It does two things. It has some kind of comparison to make a decision, right? So you execute the decision, or you do a comparison. So some kind of decide whether I want to go left or right, or I want to compare, some kind of compare function where I compare two values, right? Value 1 and value 2. And depending on what my values are, I'm going to be able to go to the left and right node. So that has some kind of compare function, right? It's still a node, still has left, right, parent, and leaf, but it's a special node. It's a decision node, and the decision node can make decisions. So it can kind of compare two values that you pass to it, and then it can decide whether it's going to go left or right. It could be a condition that it's a Boolean. Maybe that instead of my comparison could be comparing two values, and it could be an overloaded kind of function where I can say, is this true? Do I have, a line of sight? So maybe my compare function could also take in one value, right, which is a true/false value, which is some kind of Boolean value. All right, so the compare can take only one function, or it can compare two values, like a min and a max, to make that thing up. So if it takes one value, then the decision node basically says, if it's true, go right. If it's false, go left. That's what the compare does when you pass in the comparable. Okay. So Sinan says left and right node in class is a node object. Yep. These are all node objects. They're just references. Okay. So this is a type of decision node, but there's other types we're going to talk about today. Behavior nodes. We're still going to make a tree class. It's still going to be a binary balanced tree. But this time, instead of us having decision nodes that kind of do comparisons, we're going to have behavior nodes. Let's get to that. So here, the trees we're going to look at are three types. They have three types of tasks that they can perform. They can perform a condition, they can perform an action, right? And there are some kind of composite node, which is a selector or a sequence node. By the way, going back to our diagram that we have here, a decision node is one type, but there's also an action node. So class is also action node, right? Which is also a type of node. The action node is also an action, and it has a, we're going to say a execution. So we're going to say some kind of action that it's going to perform, right? Or it's going to execute an action, which is of type action. Whatever the action is. And I'm just putting this out there because there could be two types of nodes here in the decision tree. Where would I have an action node? I want to build the action node into the leaves of the tree. So I'd have some kind of action that happens here, right? We talked about this last week in a different way, right? We haven't coded it though so far, right? So I want to do some kind of actions down in here. So action, I have another action, I have another action, I have another action. The leaves are all the actions that I'm going to do, right? But this one's not an action because this one has a left and a right node. This is a decision. Okay? So the decision happens here. So decision here, action down here in the leaves, right? Let's keep going. So this is also a decision. Then at the top, the root, it's also going to have a decision, right? But down the bottom, all the leaves are actions. I'm going to take an action from there. Okay. Again, I'm decomposing this for you so we can start thinking about building it today in lab. All right. So trees, behavior trees are different in that they have conditions, actions, and composites. Okay. How do they work? A composite task, it runs each of their child behaviors in turn. Okay, in turn, kind of in, one thing after the other. And there's two types of composites, all right? So like a branch state machine. Yes, kind of, Don. The selector, right, returns immediately with a success status code when one of its children runs successfully. All right, that's what the selector node does. A sequence node, right, returns immediately with a failure status code when one of its children fails. So that's the difference between a selector and a sequence. Selector, one thing, any child is successful, it returns success. If any child is successful or fails here in sequence, it returns failure. That's the difference. All right, so here's an example of a selector node. Selector nodes usually have this question mark, and they said, okay, I'm going to do one of these things, attack. Okay, if attack, taunt, or stare, if any of these things, as an example, is successful, then this node, whatever called this behavior tree, is going to return success. I attacked, or I taunted, or I stared. It's like an OR kind of sequence, if you will. But a sequence node is a different kind of sequence node. This is a very popular way of doing things, where I kind of do something that looks like this. Is the enemy visible? Yes. Return success. Okay, cool. I can go to my next node now. I can go to the next part of my sequence. Is my enemy visible? Yes. Turn away. Can I turn away? Yes. That's success. Now go to my next step. If I can turn away, if these two are successful, then and only then can I go to the third option. Notice that this is not a binary tree. In fact, our sequence nodes are not binary at all, right? They create a sequence of events from a behavior perspective where you can create behaviors based on the type of results that you're looking for. Okay, cool. And they're tied in sequence. That's why they're called sequence nodes. All right. Okay, how about this? I want to run away. Okay, I want to run away. Excellent. If the enemy is visible and I can turn away, then I can run away. And runaway will return a success, and we're done. Okay, so we've done the sequence of actions. These are all action nodes at the bottom, right? One of these nodes, though, this one here, right, is checking if the enemy is visible. So this actually is a decision node or a trigger or some kind of condition. By the way, instead of a decision node, we can actually we can call this something else. We can also call this a condition node. Okay, decision or condition node is totally fine, right? Where the condition node itself, if it was a condition, instead of comparing, it would have a condition. And the condition would be whatever you put inside here. So again, it really depends on how you want to code it, but the decision tree, if I was making a decision tree, and we're not talking about that right now, I could have this in. I'm just changing the words up so you see what this is. But here we don't have that. We have condition, action, action. So you in a sequence, you can have conditions and actions. All right, cool. So here's the simplest behavior tree, move into the room. Move into room behavior tree would be a behavior tree of size 0 or height 0, right? Okay, so remember the question mark? This is any of the nodes returns successful. My whole thing is a success. Going back to this, if attack fails, I come back and I try to do a taunt. Does the taunt fail? Yes. I try and do a stare. Does the stare succeed? Yes. Cool. Return success. Otherwise, return failure. If all three fail, right? Here, all three must succeed in order for this to succeed. Example, is the enemy visible? No. Failure. It returns failure right away. If I can't see the enemy, I can't turn away and I can't run away, right? Because this requires that the enemy is visible. Each node requires that the previous step in the sequence, is complete and successful before I can move to the next step. Okay? So going back to a more complex tree then, if I combine a sequence and a selector, here's a selector. I can select any one of these nodes that, kind of return true, right? Let's go to this sequence first. Is the door open? Yes. Move into the room. Can I move into the room? Yes. Cool. Return success. I've returned success. It's successful. Done. I stop. I don't even go to this node, this subtree, right? Okay, let's go back to here. Is the door open? No. Failure. Goes to here. Okay. Go to this sequence node. Can I move to the door? Yes. Can I open the door? No. Failure. 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 If I fail down here, then I fail this side. This whole thing fails. Okay. However, if I said, can I open the door? Yes. Okay, now move into the room. And those are the sequence of behaviors that I can do. Each of the bottom behaviors, these bottom root nodes, leaf nodes, are either conditions, is the door open, or actions, move to the room. Now, realistically, these actions here also can return, did they complete, properly? For example, I might have an action node that says move into the room, but if I can't do it, if I'm blocked by some reason, let's say, for example, there's a guard in front of me and I can't go through the guard because there's some kind of collision, or maybe there's a timing sequence. I'm waiting. I have to be in the room within a certain number of milliseconds. If I don't make it into the room within a number of milliseconds, that means I've timed out. I can't make it in there somehow. So therefore, I return false. And if I return false, this whole node becomes false. Okay? So that's the kind of stuff that we can look at when it comes to composite nodes like this. Let's move forward. Here's a more complicated refactor tree. Okay, so where I refactored it to one thing. Because we can refactor it because notice that there are some leaf nodes here that are the same, right? For example, move into room and move into room are both the same. So what I'm saying is these two sequences are related, right? And I can refactor it so it looks like this. Okay, here's a sequence. Here's my sequence. I'm going to start off here in my selector. My selector now is part of the sequence. Okay, I'm going to go here to the left. Either one of these things, as an example, is going to be, if either one of these things is successful, then this whole thing is successful. And if this is successful, the sequence is successful. Remember, the sequence can be only one node. It doesn't need to be balanced. Okay, how about if I go here? Is the door open? No. Okay, it failed. Let's try this side. That's what this question mark does. It's a selector, either one or the other or the next one or the next one. As long as any one of the actions is successful, then I'm successful. Okay, so I failed the door open. Cool. Let's try the sequence now. Move to the door. Yes. Okay, cool. Open the door. Can I open the door? Yes. Cool. This returns success. I return success up here because one of these two nodes returns success. This whole subtree is successful. Therefore, this sequence is successful. Hopefully it makes sense. All right, let's move continually forward. Here's a behavior tree for a minimally acceptable enemy. I like this one. All right, I'll make this a little bigger for you guys to see this one. I love these ones because these ones give you a lot of information. Okay, so selector. I can do any one of these two actions, this action, the subtree, or this subtree. Each one of these can return, the first one that returns true, I'm good. Let's start with this one. Selector, sequence, right here. Okay, cool. Is the door open? No, it failed. Here, right? I'm back up to here. Okay, cool. So this side failed, but we don't care now. Let's try this side. Can I move to the door? Yes, excellent. All right, now it's in the sequence. I have to go here. Now, selector. I'm going to go to the first one first, this part. All right, is the door locked? I move to the door. Is the door locked? Yes. Cool, right? And if the door is locked, right, then maybe what this means is unlock the door. All right, that's what it unlock the door would do. Open the door if the door is not locked. If the door is locked, it should be saying, this really should say, is the door unlocked? If the door is unlocked, then open the door, right? If the door is locked, this whole thing would fail. All right, now come to here. All right, so now I'm going back to this one because this side failed. I'm going to try this side. Okay, cool. This side failed. Can I barge the door? Right? Right? If I barge the door, it returns true. Right? Is the door open now if I've broken the door down? Yes? Cool. I've barged open the door. I've opened the door somehow. Right? And I'm back to this selector node. This side succeeded. Therefore, I return success here. And because this one is successful and this one is successful, I can go to the next node, which is this one, which is move into the room. Again, it's a little bit of notation, but the idea here is that you can follow the sequence. You can follow the behavior that we're trying to design here. All right, I think this is pretty straightforward. So behavior trees are made up of independent tasks, right? And again, each task or action, if you will, has its own algorithm and implementation. We don't care about what the other actions do. We just know that it's going to have an action. All of them conform to some kind of basic interface, which allows them to call one another without knowing how they are implemented. The implementation is a black box, okay? So here is what a task or an action might look like. We want to return on success true or failure false. So I want to run or execute my action and I'll return if that execution it passes or fails. That's what I want to do. And that execution passing or failing might be some kind of condition that I'm checking. Example, do I have line of sight? Do I have line of sight? Return true or false, yes or no, right? Here is an example of the enemy near, which extends tasks. So class enemy near extends the task class, and the run, it runs this task that says return true if the distance to the enemy is less than 10 units, whatever those units are. Otherwise, return false. So basically what I'm going to return is I'm returning this, and this run action is something that I'm going to return. So this task is something that I'm going to load. All right, and here's a play animation task. I want to play my animation. It extends the task class. I'm going to have an animation ID and some kind of speed, how fast I want to run the animation, how many frames per second, if you will, where 100 is 100% of the frame rate. And maybe if I put 0.5, be half the frame rate. So if I was running at 60 frames per second, and if I put 0.5 in here, that means every 30 frames, I would run the animation tick, all right, to the next animation and so on. And then what I'm saying is, okay, run the animation. If my animation engine is ready, is it ready? Then play the animation at the specific speed. Return true. Else, if the animation engine is not ready for some reason, return false. The animation couldn't be played, okay? There's also selector, which class selector, here's a selector and here's a sequence then. So selector has a series or an array of tasks, a list of tasks, okay? So for every task, for every child in children, right? I want to run this task. For every child that's in how many children I have, right? So children of, which is the collection. Then if I can run the task, then return true. That's my selector, right? I check each one. And if one of them is able to run, then I return true. Doesn't matter. My leftmost one, if it runs, if it returns true, my whole task, my whole selector task returns true. Otherwise, it returns false, right? Whereas my sequence is working differently, right? It says, all right, so loop through for every child in my children array or list, right? If I can't run the task, then return false. Otherwise, return true. So it's kind of the opposite, okay? That's what the sequence and selector tasks are like. Pretty straightforward. All right, what about performance? So we talked about the performance of decision trees is pretty fast, right? So performance of behavior trees, it really depends on the tasks that are loaded onto it. So the more tasks, especially if I have selectors and sequence nodes and leaf tasks, conditions and actions, that's what leaf tasks are, that are O to the 1 in performance, so linear, and memory will be O to the n as an example. So again, what this means is just a way of measuring the performance based on the type of task. You'll learn more about this notation, O to the whatever, when you do data structures. All right, let's go back to non-deterministic composite tasks. So we have deterministic stuff, which we've talked about before, but we have some kind of selectors and sequences. So far we have this idea of running in strict order, and the order is defined in advance by by us. We load the tree as an example with a bunch of tasks, and then what we want to do is traverse the tree. We give it one kind of decision. We want to say if the enemy has the decision that they're going to make every round, right? As an example, okay. So what we want to do is sometimes what we want to do is we want to give probability for it to work in a certain way, as opposed to always being deterministic, right? So the way we could do it is we don't want to make it predictable. We want to make it so that we have a chance of failing. And what we can do is we can create something called a random selector. And a random selector basically says, instead of always going to the left task, let's go back up to this here as an example. Here's a selector. Instead of always starting over here, what if I started on this side, right? So I can start either side when I want to do my task. So instead of my AI always doing this side, being predictable, sometimes it'll do this side. Okay, what effect might that have? Well, if I did it this one sometimes, this side here, and because these two things are independent of each other, because they're both selector trees, this is a subtree that's a selector subtree, and this here is also another selector subtree, right? Which means each one of them, any one of them could start first. In this case then, if we start this one first, we say, okay, cool. Can I move to the door? Yes, cool. All right, let's try this out. Is the door locked? If it's locked, then return false. Yes, it's false. Cool. It's locked. Let's try and barge the door. Did we barge the door in? Yes, we did. Is the door open now? Yes, it is. Move into the room. So this works, right? We can do this task, if the door is locked. But what if the door was not locked, right? If the door is not locked, then let's open the door. If it's open, we return true, and we come back down here. And if we either barge the door, well, wait, we don't, either one of these things is good, right? If one of these is returned true, we go here and move into the room, okay? But what if both of these selectors are random selectors? So this is a random selector, so I can choose this subtree. Let me annotate. I can choose this subtree, or I can choose this subtree, right? And then this selector is random, so I can choose this subtree, or I can choose this subtree, all right? So if that's true, and if I chose this one randomly, and what if I chose this one randomly? So, okay, I go here, can I try and barge through the door, even if I don't even check if it's locked. The AI could just come right down here and say, I move to the door, I barge through the door, is the door open, right? Yes, great. If not, let's see if I can open it now, right? I try this one second as an example. I can go back this way and then move into the room. But you can see you can try different things. So that's kind of what the way it can work, right? Which is not negative. It's just more unpredictable. But you got to make sure that each of these things has a chance of succeeding on its own, right? If it has no chance of succeeding on its own, then randomization would be very challenging. All right, let's go back to further down when it comes to non-deterministic random selectors. All right, so here's the way it works. While true, if the child is equal to some kind of random choice, right, of children. I'm going to choose a random child, 0, however big the children are. If my child is run, this child, a child that I made, then return true. Otherwise, return false. Okay? And while true, keep running. Keep running. Keep trying the other one. All right, and you can have other kinds of non-deterministic composite tasks. For example, I might have a non-deterministic selector or a non-deterministic sequence where I can shuffle the way the sequence works. I can try doing something else. Like, for example, in my sequence of tasks, maybe I want to try and, instead of trying the door, see if the door is locked, I'm going to see if the door is open first. Is the door open first? No, fail. Right? I mean, so you can make it so that the AI is not always perfect. Yeah, Miguel, if you don't program it properly, the problem in randomness is you might just fail, right? That's the only problem. Your AI may fail multiple times, right? All right, so the random shuffle, what it'll do is it'll shuffle the task, and there's a shuffle task shuffle algorithm, which is in pseudocode. So here's we talk about ordering, and what this works out to be is, notice that there's additional little marks here, right? So there's this mark here, which means that this is a selector, right? And then the selector has this other task right here. Neil says, can we make different behavior trees for when the character is in idle, moving around, for example, or do you put everything in one tree? It really depends on what the goal of the behavior tree is in the first place, right? So we haven't gone to goal-oriented behavior, but let's think about this for a second. If my goal is to destroy the player, right, or find the player, I'm always searching. If that's my goal, then my goal might be something like this. Let's make some, kind of go back to our diagram here for a second, and I'm just gonna move these away. All right, so let's just hide these. Actually, let's just, for the layers, let's just flatten the layers for now, and then I'll hide them. So we can always put the layer up and all that stuff. So let's think about this for a second, right? If I have a decision, instead of a decision might look like this, but when it comes to a behavior tree, it really depends on my goal. My goal is to find the player. I know the player's around. I want to find the player. then one of the first things I might have at the top, right, is, again, what do you think I have? Do you think I should have a selector, or would you put in a sequence first? What's the first node that I would put in? If I want to find the player and destroy him, my robots, right? How would I do it? How would I structure this if we thought about the behavior as opposed to decision? So this is the decision way of doing things, where I kind of do left or right. Do I have line of sight or do I don't? How do I program this if it was going to be a behavior instead, right? Well, I can rejig the decision tree into a behavior tree by first looking at the type of node that I have at the top. Is this a sequence, right? Or is this a selector? If it's a selector node on the top, that means doesn't matter what these two things are, these two subtrees, right? So example would be check to see if I have line of sight, right? So line of sight is something that I would choose here in the decision node. If I was doing a decision node, let's program this for a second. My first thing is, can I see the player, right? Do I see the player? Line of sight, that's my decision, right? If I have line of sight, then I'm coming here. Okay, am I close enough? Right? Remember we said this last week. Am I close enough? If I'm close enough, then attack. Okay, that's the way decision works. Very fast, right? So line of sight, I'm close, attack. That's remember the attack, the leaf nodes are all action nodes. All right, do I have line of sight? Yes. Am I close enough? No. Move. So move to player, right? That might be the way I do it. And then exit. Move to player might be the action, right? Because it's not a sequence, I move to player. And then I'm outside of this decision for this round. Every round or every kind of decision that I make in a decision node, I only may do one thing, right? I only do one thing. So what happens is I go through and I decide which action or I'm going to take. I'm going to take some action. And then at the end, I'm going to return the action. That's what I'm returning off the root, the action that I'm taking. So return the action. I'm returning move to player. Returning the action, return move to player. Returning the action, return move to player. Recursively up the tree. Okay, that's what's going to bubble up, the action that I'm going to do it, right? Okay, so that is line of sight. But hold on a second, Samuel. I'm going to get there. I like your idea. All right. Okay, what about if I don't have line of sight? If I don't have line of sight and I go here, well, I want to patrol, right? And maybe if I can, as an example, maybe move to line of sight, move to a node that has line of sight, or patrol, right? And if I patrol, if that's the action that I want to take, how does that fit in with the left side of my tree? I want to be able to patrol action. I want to look around, basically. That's my action that I'm going to do, right? So I don't have line of sight, right? And the other action might be something like, in decision, is my player in radius, right? Is the player in my radius? Can I hear the player? Can I detect the player in some other way? But I can't see the player, right? That might be the decision that I'm making, right? Okay, so if the decision, sorry, I'm going to try and put this in so you can see it. If the player is not within my radius and is not line of sight, then I'm going to patrol. Left is no, right? But if the player is I've detected the player, I don't have line of sight, I can't see the player, so I can't move to the player. So the other action might be move closer to where I'm thinking the player might be, which is move to line of sight. Move to line of sight, or something like move in the direction that I think my player is in. That's what move to line of sight might be. So those are the different actions, right? I can patrol. I can't see the player. I can't hear the player. I patrol. All right. I come back to the root, right? Do I have line of sight? No. Can I hear my player or see or feel the player? Yes. I'm not going to do the patrol action this round. I'm going to move to line of sight. Okay, cool. Do I have line of sight now? Well, I moved to the thing where I thought the player was. Do I have a line of sight? No. Is the player still within my radius? Yes. Continue to move to line of sight. And that's how the decision tree would work. How about this one? How about the I'm going to convert my decision tree to a behavior tree. What selector sequence can I do? Well, I need to know a couple things. A selector is going to be either or. Either one or the other is good. All right. So let's start with the selector node on the top. Instead of starting with line of sight, we're going to start with the selector node. Okay. Not a sequence node. So selector. Cool. All right. What's my sequence? Right. And again, I'm going to make 2 sequence nodes, right? Or as an example, 2 sequence nodes, right? So there's 2 sequences. Let's start off with line of sight. So let's bring that window up for layers. Sorry, I added a lot of stuff in here. I think I'm trying to explain this in the easiest possible way. So just bear with me while I do this. Okay, so I have 2 sequences now. Sequences, remember, they look like this. They have a line and they look like an arrow. That's the sequence, right? And if you're going to draw this out in your GDD, this is what you would do. You draw sequences, right? And so there's a selector. Of course, each of these things would have different ones. The selector would be round, not square like this, but it doesn't matter. The symbols are important. All right, cool. So here's my sequence. So the first sequence is the line of sight sequence. Okay? That's what my line of sight equals. So this is, do I have line of sight? Okay? And that is going to be on this side. So this is something that I'm going to look at as an example. Let's pull this over here. I'm going to look at that from a thing that I want to map. So do I have line of sight? Yes or no? And if this is true, if I have line of sight, then I want to, I could say something like, okay, I have line of sight here. Let's go to the next part here to see it. Am I close, right? So am I close then would be some kind of additional a sequence. I can go with another sequence here, right? So let's say another sequence node, right? So we can make it so that make it as complex as you want. Let's see if we can refactor this later on. Maybe there's a way of refactoring. So another sequence node. Let's see if I can draw this better than that. So let's try this again. Take more care. Okay, so another sequence node. And remember, this one each one of these has to succeed in order for this whole thing to succeed. Okay. So I could say that the first thing is, am I close? So close is what I want. So close. If I'm close, right, then I can attack. Otherwise, what do I need to do? I'm going to get out of here, right, and go try the next side. Okay, so I want you to see how this might work. Okay, and it's going to work a little different. So if I'm close, then I want to do an attack. All right. Okay, so this is the attack. So I could do this. But what if I'm not close? Well, there is no move to player, right? If I'm close, right, is a condition, then I'd have to, if I'm not close, then this whole thing fails and I'm coming out here. This whole thing fails, then I come back out here if I'm not close, right? So this sequence here would be, okay, cool, move to player. Can I move to player? Yes. Then I attack, right? That would be the next sequence. Okay. But only if and if I can see the player, right? So this doesn't make any sense. So like, let's see if we can restructure this. So line of sight, and then the next part is, am I close? If I'm not close, right, then I want to try the next one. So this can't be a sequence. This has to be a selector, right? Because close can fail. If close can fail, I need to continue, right? Hopefully you understand what I'm saying. But let's try this out again. Let's try the brush library, and I'm just kind of thinking this through with you, right? As we're moving through, because it's an important way of doing it, right? I'm trying to convert from this to this. Okay, so it's not this, then, right? It's not this, it's the question mark, right? So it's another selector that's under here, right? So here's my selector. Okay, am I close? So close would be a selector. So if I'm not close, can fail. I'm okay with close failing, because if I'm not close, then what I want to do is some other action over here, right? Let's see if we can restructure this a little bit, right? So I don't want to attack if I'm not close. I want to move to player, right? So let's try that out. So let us these, and yeah, we'll have to restructure one side one more time. And why is it not letting me do that? Oh yeah, because I'm doing this. And let's just get rid of this. So I want to, sorry guys, just as I'm drawing, it's like I'm drawing on the board. So if I'm not close, then, well, move to player. So move to player might be something I need to do, right? If I'm not close, right? And that means that this would be somewhere down here, right? And then finally attack. Okay, let's see if this makes sense for you. So move to player, attack, that's an action. And then up here would be a sequence node. Let's see if we can restructure this so you can make heads or tails of it. So there's a sequence node, and this goes here, this goes here, this goes here. So let's take a look at this side of the house, right? And a little bit more complex. Do I have line of sight? Yes. Cool. Am I close? No. Doesn't matter. Try this side. Can I move to the player? Yes. Excellent. Attack. Make sense? Do I have line of sight? No. Fail. Okay. So that's how that would work. But if we don't have line of sight, what if I have radius, right? So now this is where I can check to see if I have radius. So let's put the radius here. And it'd be nice if we would move this. The way we made the tree is pretty tight, but it's okay. So we'll say radius. And I want you to think of, is there a way that you could refactor the tree to make it better than this, right? So radius is here. And the reason why I'm saying this is because there's more than one ways to represent the behavior matrix that we're coming up with here. So here's the behavior. Am I in radius? No. If I'm not in radius and I don't have line of sight, well, then I want to do a patrol. So this can't be this. It can't be a sequence node. It has to be a selector node, because I should be able to patrol at the very minimum some action, right? So that is something I need to do. I need to take some action. So it can't be this. It has to be this, right? Because I can fail having being in radius, right? I can fail. And if I fail, then I want to do patrol. If I'm not in radius, then I want to do patrol, which means, and by the way, it doesn't matter. Let's just move this tree a little bit aside, because to give us a little bit more room, I'm just going to grab this tree and move it a little bit aside here just to give us some more room. I want to explain this to you for a second so you can see this. So let's suppose I put the tree over here, and we'll connect it again in a second. So, okay. So I want to express this to you so you understand the issues that we have here. Am I within radius? Well, that's going to have its own things, right? It's going to have, if I'm in radius, then I don't see the player, but I'm in radius, then I want to move to the player, move to line of sight. That's what I want. I want to move to line of sight, right? That's the next action, right? So that is my next action. If I fail this, then I want to move to line of sight, okay? All right, what if I can't move to line of sight? Because look at the things I have here. Am I in radius? Well, then, no, then patrol, right? Otherwise, then move to line of sight. Move to line of sight. So how do I code this? I could very well code it like this. I could say that if I'm in radius, I can just make a sequence node, a single node that does one job, right? So I can kind of move it. Remember, my selector or my sequence can literally do just one job every single time. It's either a pass fail, a single node, right? Which could look like this. I'm just putting it out there, right? Which is if I have radius, if it passes, then move to line of sight. Okay, that might be my action. Okay, what is another way? Is there another way of coding this differently? Could you? Let's put this in there so you can see it. Okay, but what if this fails? Then I'm going to try something else. Well, I'm going to try patrolling. So you see the right side of my tree is not as nice as this one, right? So let's try this out. So here, this would be patrol. Can I patrol? Am I being stopped, by patrolling, right? So now we have to think about, is there something else? Is there something else? Another way of representing the right side? Because it looks like you have these dangling things. Patrol is an action. So if I don't have radius, then I want to patrol. So if I have radius, then I want to move to line of sight, right? That kind of stuff. I can also check other things. Like, for example, I can say, am I close? I can check to see if I'm close, if I have radius, but then I may need to refactor this tree. Okay. What other ways could I code this? Does anyone else have an additional way of doing this, right? Well, remember that the selector can do multiple actions. Am I close? Do I have line of sight? This could also be a selector sequence. If I don't have line of sight, right? If I don't have line of sight, then maybe what's going to happen is that this whole thing will fail if I don't have line of sight, and then I go to the next sequence and the next sequence and the next selector. So there's lots of stuff to do here, but you can see how behavior trees are a little bit more tricky to pull off when it comes to this kind of thing. This would be okay. This little subtree is totally fine. This I understand, but either doing this one or radius, that becomes more challenging. All right, so ordering is important sometimes. For example, I want to enter the door and then I will open the door. Or if one of these two fail, if I enter or open, right, either one or the other, doesn't matter which one, then I want to first I want to barge the door, then I want to align with the sequence, get matches, or get gasoline. One of these two has to work in order for me to make this work, right, as an example. Then douse the door, right, as an example. You can do them in either sequence, get gasoline or get matches. Doesn't matter which one I do first, right? That's what this means. But I have to have both of these in order for me to do this. If both of these don't exist, doesn't matter which order I get it in, right? Then I fail, all the way out, right? If I come to this point, if I can't open the door and I can't go through the door, then I can't. My only option is to barge through the door or to burn the door down. Okay. We also have to talk about something called decorators. And so far we've talked about conditions, actions, and composite. The other one is decorators. And a decorator, what it does is it wraps another class. Okay, that's what it does, wraps up another class. So in this context, a decorator has a single child. Notice what we went back to the patrol. That could be a single child. That's a different type of task. And so a single task is a decorator. So an example would be limit extends decorator, where the run limit is an integer, and how much did we run so far? That is, I start off at 0, and then if my run so far is greater than or equal to the run limit, then I return false, right? Because I failed. If I reach my limit, or increase the run so far and do it again. Keep running my this thing that I'm doing. Okay. I can also do a decorator that keeps running until I fail. So until fail extends decorator, And that means I'll keep trying to do something until I fail. Example, keep going back to the door, keep, turning around. I want to keep going behind I want to backstab my opponent. I want to go behind his back. I want to keep trying to go behind his back. A good example of this type of behavior is the grayling in, if you've played Valheim lately, the grayling will, which is another enemy, will always try and circle behind you to attack you. And they'll try and flank you a lot of times. They'll try and flank you, and even gray dwarfs in Valheim, they'll try and flank you. They'll try and go behind you or to either side of you, and they'll keep trying to do that and until they fail. So here's an example behavior tree with these until fail decorators. So here's an until fail, right? Where we basically say, okay, so selector, I can either do this sequence, or if I don't pass this sequence, I'll try this selector over here. So sequence, line of sight, no, fail, right? Go over here, go back to this, all right? And now I'm gonna try this side. Sequence, is it audible? Yes, creep, which means patrol or move closer, right? And then if this passes, then this passes, right? However, if it's not audible, then I'll move, patrol. This is an example of what can happen. Notice that this selector only does one action. It doesn't have a decision. So this is something that we could restructure our stuff to have as well. Okay, so like a decorator. How about this one? Okay, is it visible? Yes. Okay, until fail. I want to keep trying this until I fail. Go down to my selector. Am I conscious? Right? Yes. Okay, I want to hit, and then I want to pause, and I want to keep hitting, and I come back to this one. Am I conscious? Then is the enemy conscious? That's what this means. I keep hitting, and then I pause a second, and I hit again. Is the enemy still conscious? I keep hitting, and I pause, and I hit again, and I'll keep doing this sequence until I fail, and until one of these fails. For example, when the enemy's not conscious anymore, then it fails, then I come out of this whole thing fails, and this comes up here. Okay? Or if I can't hit, as a good example. Did I go through this tree once I finish the previous task? Yeah, I got to finish this one, then I go to this one, because this is a sequence. Sequence means I got to go from here to there, to there, to there, to there. That's how a sequence works. And all subtrees must be true in order for this sequence to pass. Whereas a selector, either one can be true. The first one, if it's not true, I'll try the next one. And only if all of them fail does this thing fail. All right. An inverter is another type of node. It extends decorator and it inverts the result. All right. Okay, that's what it does. And inverters are really important as well, because sometimes we want to do the opposite action. Okay, so we can guard resources with decorators. So example would be, here's our decorator, right? Or it's a sequence node. Is the animation engine available? No. If it's not available, this whole fails. This whole thing fails. Why is this a decorator? Because if the animation engine fails, I can't play my animation, so I protect my play animation state from failing, and I do that by checking to see if the animation is available. Animation engine is available first. Okay, that's how it works. So we test the behavior here, and if I am able to do it, then I can perform the behavior. I can do that with a decorator sequence. Okay, cool. So that's what decorators do. One thing is there's something called a semaphore, okay? And what a semaphore does, and actually it's funny enough, I read about semaphores recently again, and it was a completely different thing. Sorry, I meant as the decision tree ran only after it finishes attack, for instance, and needs something new to do. Sorry, I'm going back to Neil's comment. Are you talking about decision tree or behavior tree? A decision tree just makes left or right. It's either true or false. A behavior tree is something totally different. Yeah, a behavior tree, it runs only if it for the one that keeps on repeating this part, then what happens is until fail means that if one of these things fails, right? Am I conscious? Yes. Can I hit you? Yes. Can I pause? Yes. Can I hit you? Yes. Right? If any one of these things fails, then this fails. And if this fails, then I come to this. Until fail means I'm going to keep doing this over and over again. And when this fails, it doesn't matter. It's going to still return true. That's what this decorator will do. And then it's going to go to restrain. So if I knock you out, or if one of these stops to work, then I'm going to try and restrain you. And if this restraining fails, then I'm going to fail and try this side. Okay, that's what it means. All right, let's go back here. So guarding resources, we talked about this part, and yes, okay, so semaphores. And I was talking about semaphores. The way they work is sorry, I lost my thing here. Semaphores are a way of guarding resources when we run things in parallel. So one thing we can do with semaphores is sometimes they can be just a simple integer, right? The semaphore can start with a 0 or a 1. If the semaphore, again, think about what this is. By the way, semaphores were invented by Dijkstra, believe it or not, back in the day, right? He was creating something called the machine or the machine. And he created a parallel multitasking, multi-programming machine back in the day. In the 1960s, 1968 is if I'm not wrong. And he created something called semaphores in order for it to move from one task to the other task, so for multitasking. And the way semaphores work is they have some kind of unit, and it's the ability for us to be able to lock and unlock, as an example, a task from working. Okay, that's how it works like. So, so basically what we're trying to do is we want to ensure that some kind of limited resource is not oversubscribed. What oversubscription means is that you can't access something that is already being in use. So example, I have my animation systems in use, and let's say I can only perform, for whatever reason, if it was that kind of game, one animation at a time, right? So what it keeps is a tally of the number of resources that are available and the number of current users. That's one way of doing a semaphore. The other way of doing it is using a semaphore is doing things like I want to lock a resource and then I want to release a resource. When the resource is available, I want to release it so you can use it. Otherwise, I can lock it when I'm using it. That's what a semaphore allows us to do. Okay? It's just usually some kind of integer number, right? And the integer, as an example, the semaphore allows us to track how many users are using an object as kind of a thing, and I can lock it. If, for example, the total number of users has been reached, then I'm going to acquire a resource, right? Lock it. Otherwise, I'm going to release the resource, let people use it, okay, as an example. And this acquiring and releasing of a resource allows me to do things like I can guard resources from overuse. And guarding resources is important, especially if you're trying to do some action that is impossible. Example, I only have one door. If I have an AI that's already trying to go through the door, I don't want multiple AIs to try and go through the door, just one. If I already have an AI doing that, let's do something else. That resource is locked. That sequence is going to fail because it's not even an option, right? You can't even go there even as a random thing because I'm already on the door. I'm at the door already. I don't want another AI to try and barge the other one over, like two AIs competing with each other to get to the door so they can open it to get to me, right? I want them to try some other action, okay? So semaphores can be used to guard, not just resources, but also actions. Okay, I'm going to move on. So concurrency is parallel tasking. All right, I want to do more than one task at the same time, right? So we don't have to worry about it. Decision trees, they run really, really quickly. and they given the result that we asked for right away. It's either one or the other. It's very cut and dry. All right, for decision trees. State machines, we're going to learn about them next week. They're a long running process, but their state again is explicit. It's either this one or this one. It's very discrete what we're going to get out of them. But behavior trees are different because sometimes what happens is I can have multiple actions, and the timing is important for some sequences. I want to start a sequence. Meanwhile, another AI can be doing the same sequence, and they can clash. If I want to try and access a resource, a door, a window, a sword, the player, I want to access a resource that is not available. I can't attack the player. There's no room. Okay. An example would be something that looks like this, right? I have my decision tree. One thing we haven't had a chance to do, right, is think about, can I attack? I'm close to the player. Can I even move to the player? Well, in a decision tree, if I can't move close enough to the player because there's another AI in front of me, this whole thing is going to fail, and I'm going to come out, right? I've tried to move to the player, right? This doesn't say move to player question mark. It says move to player. It's going to do it, right? I could make it so it has an option. Did I move to player? Can I move to the player? Maybe the player's blocked. Maybe the player's inside of a cage. Maybe the player's behind a door. If that's the case, then it would be a different decision tree that I would have here, okay? But let's suppose in this simple decision tree that I always have a chance to move to the player, right? Then I do a solid decision, one or the other. But here, I'm going to do a sequence. It's do I have line of sight? Okay, no. Try radius. What if there's more than one of these things that are working at the same time, right? I have a door, I have one door, I have one player, I have one sword. Only one of the AIs can pick up the sword, not all of them, right? I have to make up a sequence to do that, or I have to wait for that resource to be available. I always like the idea of using the same pencil. So let's suppose, and Neil, I'm just going to use your name for a second. Please just ignore me, right? Or maybe I'll use Alex. So me and Alex, we're trying to write something on the board, but we only have one piece of chalk, right? And we're in a classroom. So I pick up the chalk and I'm using it to write something on the board, right? On a blackboard, not a whiteboard nowadays, right? When I'm done, I put the chalk down, right? And when I put the chalk down, Alex can pick it up and he can write on the whiteboard or the blackboard with me. When he's done, right, then I can pick it up. Okay, this action that we have is blocking, right? Because I'm blocking other actions from happening when I take up a resource. If I acquire a resource or if I reserve the resource, right, as an example, then my partner, Alex, can't use the resource since I'm using it, right? And so either they're going to wait for the resource or they're going to do another action. And this idea of concurrency and timing is important when it comes to behavior trees because of the nature of the way the sequences run. Sometimes the sequences require a resource, right, in order for them to work. They're more complex than decision trees because a lot of times they have to do with the goal of the AI. What's the goal of the AI, right? If the goal of the AI is to kill the player, right, or to find the player, the AI is always searching for the player. It's a different goal than I'm just going to patrol. Do I have line of sight? No, keep patrolling. Can I sense the player? No, keep patrolling. It's a different thing altogether than search for the player. I know the player is around, right? Okay, so behavior trees are only compatible with actions that complete instantly. Unlike most actions, we like to schedule in the game, right? They must complete instantly. If they don't complete, bad things can happen and all this kind of stuff. And this is where we can add in these locks and unlocking states. So waiting might be something that we want to do. We create something called a pause task, where I basically can wait until something is ready, and then I can go ahead and do it. So, okay, I see the player, but I don't have access to the player. I can't get neither player, so I'm going to wait. I can also wait not on a condition, but random amount of time. For example, one of the things we've asked you to do in assignment 4 is move behind cover, wait a random amount of time, and then come back out into cover. Do I still have line of sight? Yes. Fire at the player. If I don't have line of sight, then let's find the player again. Where's that player? I moved into cover so I don't die, right? Because the player was firing his bullets at me, right? But now when I come back out of cover at a random interval, do I still see the player? No. Do I still have? I know the player's around because I detected him. Is the player within my radius, or have they run away? If they've run away, I've got to patrol. I got to find the player somehow, right? So parallel tasking can happen, and the parallel task can happen, and what it does is it happens at the same time, where I do a concurrent task, and all of them happen simultaneously. And this is a very challenging thing to do. I'm going to talk about it briefly, but it's out of scope for what we want to do in this course, right? So can we do parallel tasks? We can, but parallel tasks only happen when in a very complex environment, and we're going to make it so that they're not complex. So can you use behavior trees for assignment 3 and 4? You can. Should you? Yeah, they're totally fine. You can use any one of the 3 things that we made available. You can make it with state machines, you can use decision trees, or you can use behavior trees. Any one of those things are totally fine for you to be able to kind of create a behavior for your AIs for assignment 4. Okay, so I'm not going to go through this. Let's just give you some pseudocode on how parallel tasks work, okay, and when it comes to concurrency and timing. One thing I want to look at now as we go forward, so I'm going to keep going out of here. One thing we can do is we can convert a state machine to a behavior tree, but one thing we can't do a lot of times is create a behavior tree, or we can make a behavior tree out of a state machine, but sometimes not always possible to create a state machine out of a behavior tree. We'll talk about state machines next week, and you'll understand why. Okay. All right. I think I'm going to skip through this part because it still talks about concurrency and timing, and I think I want to move by this part to this part here, which is adding data to behavior trees. So a lot of times we have some kind of data that I want to pass in. For example, I might have some properties or attributes that I also want to pass into the behavior tree. And what I want to do is I want to say something like, okay, here's an example of a function, smoke out. Matches is fetch matches. Okay, gas is fetch gas. Douse door is go to the room door and gas. Douse door, each of these things, these subroutines, if you will, are different trees, right? And they can return true or false as an example in order for you to be successful. So here's again going back to the selector node or the sequence. Is the enemy visible? Okay. Select an enemy. Right? Right to blackboard means kind of like I want to, I have an enemy that I want to select. That's the enemy. Cool. And then I have the ability for me to do one of these 2 things. Okay. So this task here is high ground available? No. Well, then that's okay. This is an always succeed task. So then I'm going to go here to the enemy and engage the enemy. However, if high ground's available, sometimes I want to be able to move to high ground and then engage the enemy because it's a better way of doing things. The always succeed task means I'm going to return true. Regardless of what's happening here, this selector is always going to return true in order for me to check to see if I can have my high ground is available. So it's another way of doing things. Again, what we're trying to do here, guys, is trying to organize a way of getting your AI to have some kind of thinking behavior, right? So where the AI can make decisions that are more complex than yes or no, okay? It's not so clear, cut and dry as, do I have line of sight or not? It's more like, okay, I want to do a sequence of events, and I can be as complex as I want to. A lot of times we want to do all this mapping out first. Actually, all the time, we want to do all the mapping out first before we ever have a chance to code this stuff. Because if we tried to code this first and then try to map it out, we would do a lot of rework. We don't want to do rework. Remember, you guys get measured on rework a lot of times in the real world, right? If you're a software developer and you keep on rewriting your code over and over again, you know, and your senior developer is going to look at you and go, you know what, I've been doing your code reviews and doing a lot of rework here. You're Are you actually planning anything? Are you writing out your classes? Are you doing any kind of pseudocode or diagrams or anything? Flow diagrams for your for writing your code? And if you say no, I'm just kind of like shotgun programming, spraying and praying to see that it works. That might be pretty bad, right? Let's take a look at that Gamma Sutra article really quickly now to round out the afternoon or the morning. So the Gamma Sutra article is here, and it's actually a very good article that I recommend you read in more detail than I'm going to go through right now. All right. But one of the things it talks about is different kinds of nodes. They are talking about this project called Zomboid, right? Where they're running into some kind of behavior. One of the things they talk about is data-driven versus code-driven. And data-driven is by far easier to pull off than code-driven. If I have a number that I got to compare, it's a very quick decision, true or false. If I compare between these two numbers, which one is greater? I can do that, all right? Or which one is lesser? I can do that. Which one's the minimum? Which one's the maximum? Or does this number fall between these two ranges? Or do I have it or not? Do I have line of sight or not? True or false, right? Those things are easy to figure out. Code-driven, where I always get you guys to do if statements, that's bad. Code-driven is like hard-coded. Please, that's a bad thing to do. So one of the things it talks about here is, when it comes to behavior trees, is tree traversal and how trees work. They don't work like decision trees. And they don't have to be balanced at all, if you notice my diagram, right? They can be they can behave a lot differently than it can be deeper on one side than the other, and it really depends on the kind of behavior you want to program, right? So again, the three flow states are success, failure, and running. If my task is still running, then I want to keep doing that task. However, if I get to failure, I want to stop, or I want to move on to the next type of node. All right, that's what this thing means. So here's your composite tasks. I have composite, leafs, decorators. Okay, those are the three types of things we have here. Composite task we talked about before is either a sequence or a selector, right? A decorator is something that wraps a task, and a leaf is usually an action or a decision. Okay, that's what the leaf does. So here's an example of a sequence, and they mapped it out for us, remember? Okay, walk to door. Can I make it to the door? True or false? If it's true, I return success. If it's false, I return failure. Well, what about the sequence node? What state is the sequence node in when I move from walk door to open door to walk through door to close door? It's in progress, right? Remember one of the three states that you have, that's way up here. Either it's success, it's failure, or it's in progress or running. If it's running, I'm okay. I'm still able to continue with the sequence if my state is running. As soon as all of these actions or decisions have been passed through from one action or decision to the end, to this one, to the rightmost action, as an example, in order, then my sequence is successful, and I return success back up the chain. Okay? And it talks about that here. Sequence, walk to the door, success, sequence, running. Open door, success, sequence, running. Walk through door, success, sequence, running. And keep doing that. Close door, success, sequence, success, when I run to the last part. And I think that's a great way of looking at it as well. Here's more complex ones. Sequence, am I hungry? Yes. Okay. Do I have food? Yes. Are there no enemies around? Yes. Eat the food. Any one of these times, if you say no, the whole sequence fails. Am I hungry? No. Okay, stop all this. We don't need to we don't check to see if you have food if you're not hungry, right? If my enemies are around, well, even if I have food and I'm hungry, but if enemies are around, I'm not going to eat, all right? Because that means that I put myself at risk, right? The inverter node. So the inverter node we talked about before is perfect in this position. Whereas, okay, am I hungry? Yes. Do I have food? Yes. Inverter. Are enemies around? No. Then true. Return true. So if it's false, then this returns true. If it's true, then this returns false, and the whole thing fails. Okay. And that's the inverter node. And again, here's a more complex door sequence, right? Where I go from a sequence, walk to the door, cool. I'm going to my selector. Selector, again, means I can go through any one of these three things to make it work. So can I open the door? No. Okay. Sequence. Can I unlock the door? No. Selector. Can I smash the door? Yes. All right. Yes, I smashed the door. Okay. Somehow one of these three things, whether I open the door, unlock the door, or smash the door, I'm going to walk through the door at the end and finally close the door behind me. Wait a minute. Can I close the door if it's been smashed? No. Right. So that might be something else you have to kind of fix, right? It's something that you have to think about. And then there's more complex ones, which are really interesting to see. That's why I like looking at these diagrams where, I go to these two sequences, but there's a selector. Either this sequence can pass or this sequence can pass. So sequence, walk to the door, open the door, unlock the door. Let's say the cell fails. I come back to here. Okay, well, walk to the window. If the door doesn't work, try the window, right? And that's why it's really great to look at these things. And they have an example here of Zomboid NPCs. Let's see if I can play it with no sound, where they actually do, these things where they walk around and they do the thing. They've been programmed with a behavior tree. Okay. By the way, for movement and stuff, there's nothing wrong with using pathfinding, right? So, for example, I want to go to the door. I want to pathfind the shortest path to the door based on the obstacles that are in the way. I want to go around the obstacles and I want to move to the door, right? So pathfinding is not something you can't use. You can totally use pathfinding alongside, behavior, right? And it talks about different kinds of decorator nodes, an inverter, a succeeder, a repeater, right? These are kinds of decorator nodes, repeat until fail. We've seen those ones and so on. Okay, so take a look at this. I'm not going to go into more detail than this. I think there's some really great information here for you guys to look at. It'll help you make a decision, no pun intended, whether you want to use decision trees or behavior trees. Miguel says, what is the best approach for movement? Do I think pathfinding is a good thing? Well, it really depends, Miguel, on the type of environment you put together. And this is just to answer your query. If your environment is full of obstacles, right, then pathfinding is a lot easier than using things like an obstacle avoidance in other ways. And the reason for that is because, if you're pathfinding a way to the door, right, and you're going around a desk, you don't want to use things like line of sight and, weird, kind of movement patterns, right? We'd want to use pathfinding for that so that you can find the closest path to the door, right? Based on the knowledge, the knowledge that the AI can see, right? If the AI can see the door, if there's line of sight to the door, as an example, then you want to pathfind to the door, okay? If there's line of sight to the player, I'm going to pathfind to the player, all right? I can also use pathfinding in terms of nodes. So sometimes what I want to do when it comes to pathfinding, instead of using a grid-based pathfinding mechanism, right, I might use node-based, which is a lot more fluid, right? But it takes a little bit more careful planning. So node-based would be more like, okay, so I have all these nodes. These are only the places where the AI can travel, and I'm going to go to the closest node, right? And I'm going to follow these nodes to get to the player as opposed to this grid, right? Because I don't want to sometimes make a whole grid if I don't have a grid layout. A good example of that is if I'm doing 3D games, right? A lot of times I may not have a grid in 3D, but I might have several nodes. I might have kind of like these checkpoints, if you will. And I want the AI to go through a bunch of checkpoints when it comes to pathfinding. Or I might use something called, in 3D, something called a nav mesh, which, remember, it breaks down and sections off my world into different smaller regions, right? So I go from one mesh to the next mesh. And whether it's pre-baked, so my mesh is pre-baked, I make the mesh for the entire world first. I map it out and I kind of decide which nodes are going to be there. Or if I bake it on the fly in real time, right? Where I go to a room and then I bake a mesh. Okay, now which nodes are available according to the vertices in the room? the floor, right? And the obstacles. Sometimes a nav mesh is really good as well. We've kind of touched upon nav mesh from pathfinding perspective. We actually haven't done it in real time, and you'll have a chance to do that with Unity, and we showed that Unity example for nav mesh. So it's up to you how you do your movement. If you use pathfinding, or if you do seeking and steering behaviors. Seeking and steering behaviors might work as well, but the challenge with seeking and steering is if there's a whole pile of obstacles and things that can make an object collide, and if there's speed involved and those kind of things, then seeking and steering behaviors may not be as easy as just doing pathfinding, right? Pathfinder will give you the exact shortest path. Seeking and steering behaviors, what they're going to do is they're going to try and lead you as close as possible, right? But it's not going to be as accurate. If you want it so it's less deterministic, then you want to use seeking and steering behaviors in general, right? Because steering behaviors are less deterministic than pathfinding. Pathfinding is very deterministic. You're always going to get the shortest path to the player, right? So, so it really depends on your AI. I think the answer is it depends. And I know that's a nebulous answer in some ways, but I think the great thing about that is that you cannot kind of paint. There's not one golden, nugget or golden bullet, if you will, silver bullet. There's no silver bullet to find the answer, right? Can you use a combination? Absolutely. There's nothing wrong with using behavior and decisions, depending on the type of AI, or a combination of behavior, decisions, pathfinding, and steering behavior. All right, as long as it makes sense for the type of game that you're making. But again, the more you do those kind of things, Neil, then the more complex your engine is going to be when you make it, right? So, because it's going to have to support all those 3 things or 4 things. All right, that's really the lecture for today. Just a reminder again that as we approach next week, right, next Sunday is assignment 3 is due. Please make sure, if you haven't had a chance to already, that you sign up for assignment 3 groups. And if you have a problem with groups, please see me during the lab so I can fix you. Otherwise, that's it for today, guys. March 28th. March 28th. So next Sunday, not this Sunday. This Sunday is the 21st. Next Sunday is the 28th. Okay. All right, guys, that's it for me. Thank you so much. I'll see the other people in lab in about 18 minutes. Otherwise, I'm going to keep this channel open from a Zoom perspective. I'm going to stop the recording. All right, thanks, guys.